Good afternoon and welcome here to this live event. My name is Clemente Talarico, and with me as presenter we have Mr. Peter Stones. As well, for technical support we have Mr. Per-Åke Björnstedt. I'm pleased to announce here the start of a new presentation program which will happen every third Friday of the month at 14:30, as this time we are having now, European time, via live event. The first presentation will be the one starting in few seconds with the title, "Why can't you weld stainless?" Good question. We will be very happy to answer your questions at the end of the presentation, which you can type in the Q&A box, which you see on the top of your screen, on the right side of your screen. So we intend to present on about 30 minutes and take 10 minutes more for answering your questions. Okay, so enough now, and let us start the show with Peter presenting his presentation. Enjoy.
Good afternoon, everyone. I hope everybody can see the screen and everybody can hear my voice. It's my pleasure to be here this afternoon. As Clemente said, we've got Per-Åke here, who's the global product manager for these products for ESAB, as technical support in case there are any technical questions that we can't answer. We will be giving our email addresses at the end of the presentation for you to please take a note of them and feel free to email us anything that you think of after we finish the presentation. So we are part of ESAB, we're part of the ESAB Specialty Alloys division, and we're very pleased to welcome you to the first live event webinar that we're doing one a month this year, as Clemente said. So why can't you weld stainless steel? So in this presentation, what I want to give you information on really is the basics of stainless steel. What is stainless steel and what gives it their properties? Why is stainless steel stainless? We hear about the major groups of stainless steels. We talk about austenite, ferrite. What are they and how are they formed? And how do the various alloys of stainless steel affect the properties, the physical properties, their corrosion resistance properties, and their weldability? So again, the different phases, how do they differ in terms of weldability? And most importantly of all, is what happens when you exceed heat input and into past temperature recommendations. This is a crucial thing with stainless steels. The more highly alloyed the steel, then the more important that is. So I hope that makes sense. So we start off with, what are stainless steels? Well, there's a phenomena with an ordinary steel. If it has 12% chromium in it, then the chromium, the free chromium on the surface, will react with air and form a chrome oxide layer. Now, the diagram makes it look like the chrome oxide layer is 3 millimeters thick, whereas it's microns thick, but it doesn't have to be any thicker than that. It's a very passive layer that resists corrosion. So rust that you would get on normal mild steels and chromium steels, you don't get that corrosion with chromium oxide, providing that the surface of the steel is in air, is in atmosphere. Then should that chromium oxide get removed for whatever reason, whether it's been wiped off mechanically or there's been some corrosion on it, if the raw material, the base material, is left in air, then the air will form the chromium oxide. The oxygen in the air will react again and it'll reform the surface of chrome oxide, and it will maintain its corrosion resistance. Now, when you start to look at the metallurgy of stainless steels, you always get hit with these types of transformation diagrams. And what this is representing is Basically, the x-axis, the y-axis, sorry, is the temperature. So up at the top, this is liquid. This is liquid metal. And along the x-axis is the composition of the alloy. So it's using these terms called chromium equivalents and nickel equivalents. And I'll go on to show you that later on. But in terms of these diagrams that get a little bit scary, you can see the definition of them: a solidification mechanism of austenitic stainless steel with ferritic austenitic solidification mode in the interdendritic region of the primary ferrite, blah, blah, blah. Austenite forming elements. So depending on the chromium and nickel content, along with some other alloys, determines the amount of austenite, the amount of ferrite that's formed from the liquid phase when it cools down to get into the solid. To illustrate it a bit in more simple terms, we use this thing called the Schaeffler diagram. And this is good because it actually defines what a chromium equivalent number is and what a nickel equivalent number is. So from lots and lots of empirical testing over the years, these phenomena have been discovered. So it's not just chromium in itself that has the chromium effect in the alloy. So you also get some effect. Basically the same kind of things happen with silicon and niobium. So there's a formula there, so you just come out with a number. So the chromium equivalent is 28, 32, whatever. And the same with nickel equivalent. So things that have a similar effect to nickel in the alloys are carbon and manganese. So again, come out with a number. So here you can see common grades that you will have come across before. So 309, for example, 309L. That falls within this range here. We've got somewhere between 10 and 20% ferrite. That's what these lines are. They determine the amount of ferrite from 0 ferrite right up to 100% ferrite. So obviously over here you've got 0 ferrite, so you've got an austenitic steel. Over here you've got 0 austenite, you've got 100% ferrite, so you have ferritic steels. Okay, so again you can see things like 316s, a 316L, and duplexers. Now duplexers are the subject of a whole topic on their own, and they're actually the topic of next month's presentation. So you can see where that falls on the scale. It's right in the middle between 50% austenite and 50% duplex, which is what 50% ferrite, sorry, which is what it's supposed to be. Okay. So in terms of these groups, the composition of these groups, the austenitics can have between 12 and 27% chrome, 7 to 25% nickel, and up to 5% molybdenum. The ferritics, you've got a lot of chrome and no nickel or molybdenum in there. Martensitics, the same. But you can see the difference between the ferritics and the martensitics is the martensitics have more carbon. It's a higher carbon content, and that really does affect the properties. Duplexers, as we say, it's very similar to the austenitic group. While we say austenitics, those austenitics that we're talking about here with the 308L, the 316s, they're not 100% austenitic. They do have some ferrite in them. As we saw on the Schaeffler diagram, you can see that there's a certain percent of ferrite in there. So it's the way that the material's manufactured determines the amount of ferrite that's going to end up in the final melt. So specialty super austenitics, like a 383, for example, you're talking usually more than 20% of chrome and various amounts of nickel and molybdenum. And to go into a little more detail, looking at a micrograph. So this is under a microscope looking at an austenitic stainless steel like ESAB 308L, which would be exciton 19.9. So that's 19 chrome, 9 nickel. Okay, so the amount of ferrite that you've got there is between 3 and 15. So the white that you're looking at is austenite, and the black lines are the amount of ferrite in there. And this is constructed of what's called face-centered cubic molecules. So you can see these are fairly tightly packed. There's not a lot of room in there to allow other things in. So we call interstitial atoms. So smaller atoms that can get in the way and basically ruin the structure of this austenitic. So it's a fairly strong bond, and it's a fairly strong shape. So that obviously has an effect on the properties of an austenitic stainless steel. So to list the properties, really, they are easy to produce. In terms of stainless steel, they are easy to produce. They don't have a lot of ferrite in them. It's ferrite that's magnetic. They don't have a lot of ferrite in them, so they're non-magnetic. One good thing is that they are able to be formed, so they're quite ductile and strong. So the strength of stainless steels is another good reason why people use them in manufacture. And they can be strengthened by cold working. And they're also represented by, even at low temperatures, they do have a high toughness. Transferring that over to weldability, the austenitics, the 300 series, have excellent weldability even in thick sections. That being said, you wouldn't expect to use a preheat, and you wouldn't expect to use a post-weld heat treatment. Okay, so one thing to bear in mind for a welder that's new to welding an austenitic stainless steel is the thermal expansion. This is quite surprising if it's not expected, not anticipated, not known about. The thermal expansion of the 300 series austenitic is 50% greater than carbon steel. So if the welder's been used to welding carbon steel and tacking it up, tacking it together with a certain amount of restraint, then things can all go very badly wrong if he starts to get austenitic stainless steel warm. So it has to be taken into consideration. As with most of the grades that we're talking about here, low heat input, low interpass temperature. So comparing that with a ferritic stainless steel, and we're talking something like an ESAB rod 430 LMB, this is 100% ferrite. Okay, and what you're looking at here is the difference between base metal and weld metal. So obviously the difference here is this has been heated up, this has been made molten, and then it's cooled down again. And what's happened is the grain structure has opened up. Grains grow when you heat them up. Okay, the ferritics are represented by a body-centered cubic. So if you remember, the austenitics were face-centered cubic, which basically had another molecule in each of the spaces. Oops. In each of the spaces. So the thing is with ferritics is they're not as they don't have the ductility of the austenitics. They do allow these interstitial atoms, interstitial molecules to get in the middle of these, and that has an effect on the properties. Ferritics do have properties similar to mild steel, but with a better corrosion resistance. And the difference is really that a carbon steel is obviously ferritic, but the difference with a ferritic stainless steel is that it's got anything up to 17% chromium, so 12 to 17% chromium. And because of that, they are a stainless steel, but they're relatively inexpensive because of the low nickel content. They selectively attack by certain media, but they're very resistant to corrosion cracking. Okay. The good thing about ferrite is that it's very kind on, say, dirty steel. So steel base metals with impurities in them, ferritics are very kind with that. The ferrite will actually dissolve things like phosphorus and sulfur. So traces of phosphorus and sulfur that could kill some welding, ferritics are actually fairly kind on that. One thing to watch out for is this transformation between 550 and 900. You get this generation of a sigma phase. So the sigma phase appears as dots on the microstructure. and they are patches, basically patches of low mechanical strength and low corrosion resistance. So you've got big areas in there that are precipitated from within the material itself. And if these get too big, then basically you've got no corrosion resistance and very little strength. Okay. In terms of weldability, they're not as weldable as austenitic and not very weldable in thick sections. And the reason is because of this grain growth. The grain growth you saw on the photo here, the grain growth is quite significant, and basically it wants to crack. Okay, so big grains means lack of toughness. And if you've got lots of heat in there on a thick section that you're not controlling, then you'll get the carbide precipitation. So we weld them with matching fillers or even 300 series or nickel alloys. Duplexers. So this is obviously a combination of austenite and ferrite, hopefully in the region of 50%. What you can see here is the lighter color is the austenite, and again the darker crystals, the darker shapes are ferrite. So we're talking something like ESAB 2209 or Exciton 2283L. One of the key properties of a duplex and why people use them is the strength. You've got a lot of stainless corrosion resistance, but you have twice the strength, twice the yield strength of an austenitic stainless steel. So that combined with the resistance to stress corrosion cracking makes it very useful, very beneficial in a lot of applications. In terms of low temperature toughness, then it's you don't buy and use duplexers for low temperature toughness. Okay. In terms of manufacture, yes, it's a complex metallurgy, and people need to be aware of the phase balance. If you're losing the phase balance, if you don't have a 50-50 or at least a 65-35 balance between the austenite and the ferrite, then you've not got a duplex and you won't get all of the properties that you need. The other thing, the maximum working temperature is limited to around about 300 degrees. The good thing is, in terms of weldability, is that they are very weldable, even thick sections. And again, we wouldn't suggest using a preheat or a post-weld heat treatment. And the heat input and the interpass should absolutely be staying within the recommendations. For some duplexers, a 2709, 2775L, for example, which is a hyper duplex, so it's very highly alloyed. The heat input needs to be below 0.8 kilojoules, for example, and the interpass temperature needs to be below 100 degrees C. Again, in terms of for the welding engineer and design and the application, then the design of the joint needs to ensure that the root gap needs to be larger than you would normally use for an ordinary stainless steel. The problem is that the weld pool is not so fluid. The high alloy makes the weld pool quite like chewing gum, so it's a problem, and it's something that welders really don't like. We do have a product with additional silicon in there that gets away from this problem, but that's again, that's the topic of another live event. So it's something to be aware of. If you have very small, very thin, narrow root gaps, then the welder will have an awful lot of difficulty in trying to get penetration and trying to get the flow of the weld pool into it. Okay. Super austenitics. So these are 100% austenitic. There's no ferrite in these at all. So we're talking something like a 383 or Exciton 27314 LCU. So this is very highly alloyed. We're talking 27% chrome, 31% nickel, 4% molybdenum, with copper in there as well. So these are typically characterized by very big grains, and because of that, all these materials want to do is crack because of the big grain size. So the attention to detail in terms of preheat and post-weld heat treatment and using low heat input has to be absolute. Okay, the design of the weld bead, flat to convex. Okay, and we've mentioned interpass there as well. So all these things want to do is crack. So it is obviously possible to weld them, and people do it all the time. But it's not something that you'd want to leap into as the first time you'd ever welded stainless steel, for example. The last one of the bunch that I'm talking about is martensitic. So again, these have got 0 ferrite, but they're 100% martensite. And the thing about martensite is that they can be hardened and tempered just like a plain carbon steel. Moderate corrosion resistance, similar to ferritics, because they've got anything up to 13% chromium, but a higher carbon content. Martensistics are used because of the mechanical strength, the hardness and corrosion resistance. You can get some precipitation hardened grades that can be hardened even further with special heat treatments. But the reason that the people use the martensitics is that they're hard and brittle, so they have good high temperature strength. But because of that, they've got poor low temperature toughness. In terms of weldability, it's comparatively poor. There's always hard and brittle zones. Okay, so preheating, stress relieving, slow cooling, control of the temperature through a martensitic steel is absolutely vital in order to keep the stresses low. If it cools down differential temperatures, you've got a gradient across the alloy, then you'll get stresses building up and it'll want to crack. Again, people do use 300 series or nickels to weld them. So in terms of corrosion resistance, this illustration shows you the difference between, say, on the left-hand side, a 316 stainless, and on the right-hand side is a super duplex, a 25% chrome super duplex. So this is a typical stainless corrosion test, ASTM G48. So we're talking 6% ferric chloride at 80 degrees centigrade. You can see the 316 has suffered enormously. You've got bad corrosion on all the surfaces. It's eaten away at the edges, and you've got very bad pitting. And then the 904, the SAF 2304, which is a lean duplex, the SAF 2205, which is a standard duplex, they all suffer to a lesser extent than the 316. But then you can see the super duplex, in terms of pitting corrosion, is not touched. Okay, so it's just a quick illustration to show you the differences that it makes. What happens with too much heat? The photograph on the left looks like a very nicely TIG welded pipe. However, on further inspection and micrographs, you can see the structure on the photograph on the left hand side is the normal microstructure. That's what it should look like. Whereas actually, because it's been taken to too high a temperature and it's kept there for so long, you have precipitation of carbides at the grain boundaries. So the carbides have come out of the alloys, basically out of the grains, and they're precipitating at the grain boundaries. So you have very carbide rich grain boundaries. This is called sensitization. Okay. And it makes the weld very, very susceptible to intergranular corrosion. And it really does not take that long. So at temperatures around 750 degrees C, if you're not very careful with the heat input and the interpass, then on the face of it, what could look like a very nice weld is actually not very good in terms of corrosion resistance. The last slide I want to leave you with, I think I'm just about on time, is the effect of post-weld cleaning. Again, this graph illustrates the differences between the various post-weld cleaning has on pitting corrosion resistance. So the G48 slide that we saw with the 316 being completely rotten away, if you do these kind of treatments to it, then that will happen to a lesser extent. Okay, so if what you see on the right hand side, number 6, is basically a wire brush. Okay, and on whatever scale we're using, you can see the difference between, say, between 6 and 5. There's a factor of around about 3 times. So if you grind it, if you grind a weld, make everything as smooth as you can with a grinding wheel, then you'll increase the resistance to pitting corrosion by a factor of 3. Number 4 is a final polish at 120 mu. Number 3, number 2 is 360. The best thing we would recommend is to pickle and passivate. Okay, this makes sure that all the, if you like, all the sharp edges have been removed, and if you passivate, then you're going to reform the chrome oxide layer. So in terms of just wire brushing your weld, compared to pickling and passivating, we've got a 10, 12, 15 times better resistance to pitting corrosion. Okay, so that's all I have for my presentation. Thank you for taking part. Please see my email address and Clemente's email address there. Should you have any questions, any comments, we will happily receive them. The presentation is being recorded and will be put onto the ESAB YouTube channel, should anybody wish to see it again. But please take advantage of our contact numbers and emails, and should you have any questions after this presentation, then please feel free to contact us.